So today we're looking at chapter 2, section 2.5. Let's discuss continuity. All right. Now, what does it mean for a function to be continuous at the number a, for example? All right. So if you look here, they say the limit as x tends to a of f of x is equals to a. All right. So now, yes, this statement here is enough to say that this function is continuous at the number a. All right. But there's so many things that we can deduce from this limit here. All right. The first thing you notice is, I'll just get a different color. Notice it. We should be able to evaluate f at a. So it means a should be in the domain of f. All right. Because a is not in the domain of f, then f of a will not even be possible in the first place. I remember when I said the limit as x approaches a of a function, what does that mean? It means the limit from the left and the right must be equal to some number L, and only then can you conclude that the limit as x approaches a of f of x is equal to some number L, after testing from the left and the right. So you see there's three things then. The limit from the left and the right must exist, and they must be the same. The function itself must be defined at that number a, and the limit must be the same as the function at the number a. All right, those are the three conditions for continuity. There we go. These are the conditions. And guys, if I ask you my test, there's the three conditions for a function to be continuous at the number a. This is what I'm asking you. Don't tell me anything else. So first thing is f of a must be defined. Very, very important. It means a needs to be in the domain of a. So f of a must be defined, right? If I ask you, is this function continuous at a number a, and you plug in a directly into that function and it's undefined, then you conclude that you don't even need to test number 2 and number 3, all right? If any of them fail, then you conclude that that function is not continuous at that number a. So we say it's discontinuous at a, all right? All right. The second condition is that the limit as x tends to a of f of x must exist. Remember, for this limit to exist, what does that mean? It means that the limit from the left must exist, the limit from the right must exist, and they have to be the same. All right. So the limit from the left must be the same as the limit from the right, and they have to be the same. So you have to be equal to some number L. All right. And then the last one says the limit as x approaches a of f of x must be equivalent to the function at a. All right. Now someone asked the question, how does 1 and 2 differ exactly? Now for 1, I'm directly substituting the number a into the function. For 2, I'm using limit. Remember, when we talk of limit, it means we don't care about the number a itself. We're just looking at what happens when we approach from the left and the right. We've done that many times where, for example, let's say we had a sketch like this, and then there's another piece of that sketch down here. All right. If you notice it, if I say that this number here is a, the first thing you're going to notice is, so I'll put a little closed dot here. I think this should be the best explanation. So here you have a closed dot, and then down here you have some sort of open dot. All right. Now, f of a exists because you can see it's a piecewise function. All right. You have different p's depending on the value of x. F of a exists. The limit as x approaches a. Now, if you check here, when you approach a from the right, you're going to get some value there, y1. When you approach a from the left, notice it, you're going to get a second value up there. These two numbers are not the same. Already, that tells you how 1 and 2 differ. The limit can exist, but f of a is not defined. F of a can be defined, but the limit does not exist. Why? Because the limit from the left is different from the limit from the right. And it's true most of the time when you get a piecewise function. All right. Piecewise function, it can happen that f of a is defined, but the limit itself does not exist. Hence, you don't have continuity. All right. Okay, so we say that if f is defined near a, all right. Remember, when I say near a, we're looking at some values close to a, not a itself. then we say that f is actually having a discontinuity. So for example, if f of a is defined, but then your limit as x approaches a does not exist, you say the limit or continuity is not defined, so we say it's not continuous. What does that actually mean? It means discontinuity. So discontinuity simply means that it's not actually defined. All right. So it means that the limit either does not exist, of f of a is not defined, or f of a is different from the limit as x approaches a. All right. If a function is not continuous, then we say it is discontinuous. All right. All right, so let's look at this. I think this looks like the one that I was explaining, the example that I used just now. Now, they say at which number is f discontinuous? All right, at which number is f discontinuous? Now, let's look at the points of interest. So we're going to start with 1. Look at 1. Is f of 1 defined? The answer is no. Look, there's an open dot there. Open dot means it's not included. It means f of 1 is not defined. What did I say? You don't test property 2 and property 3. Automatically, you say it's discontinuous at x equals to 1. Let's look at another number of interest. Let's look at 3. At 3, f of 3 exists. It's defined. F of 3, can see there's a solid dot here. This solid dot means f of 3. So f of 3 exists or is defined. But the challenge is that the limit as x approaches 3 does not exist. Why? Because when you are approaching 3 from the right, look there, you have some value up there. You're going to get some y value there. When you're approaching from the left, you're going to get some y value down here. You see those two numbers, they're different. Because the limit from the left of 3 and the right of 3 are different, you say that the limit does not exist. So property number 2 fails. And in conclusion, we say that it's discontinuous at x equals to 3. All right, let's look at 5. At 5, f of 5, okay, 5 is a very tricky one. Guys, you need to pay attention. F of 5 is defined. There we go. That is f of 5 is defined. The limit as x approaches 5 exists, right? Because when you approach 5 from the right or from the left, you end up with the same y value, all right? You end up with the same y value there, all right? So the limit as x approaches 5 actually exists. But the challenge now is property number 3. Property number 3 says f of 5 must be the same as the limit as x approaches 5. It's not true, right? Because look at where x of 5 is. Some y value right up there. So you're going to get some y value right up there. But the limit as x approaches 5 is somewhere down here. You see, they're different. Property number 3 fails. You conclude that there is a discontinuity at x equals to 5. So in conclusion, if this was an assessment, you're going to say is discontinuous at the point x equals to 1, x equals to 3, and x equals to 5. All right. Or in other words, if I ask, okay, where is this continuous? So in this question, I ask you where is this discontinuous. You can quickly tell it's 1, 3, and 5. But typically, what I'm going to ask you is, where is this actually continuous? So if I turn the question around and I say, where is it actually continuous? You need to tell me that it's continuous everywhere except. So you say x element of real number x is not equals to 1, not equals to 3, not equals to 5. All right. Or you can say from minus infinity, it's continuous from minus infinity to 1, from 1 to 3, from 3 to 5. You use open intervals, and from 5 to infinity. So you exclude 1, 3, and 5. All right. There we go. There they say f of y is not defined. So we know why at 1 there is a problem. We also saw that at 3 there was also a problem because the limit does not exist. All right, someone said, would you use I naught or you use an or? All right, so it's a union of different intervals. So you use or. So you use union. You use this guy. All right. Remember, intersection means you adding intervals together, and that interval needs to be some sort of continuous interval. But the fact that I'm putting together discontinuous intervals. So they say, so if you look at 1, at 3, at 5, these numbers itself, they're not included. So the only way to measure this is to take this, they say union this interval, union this interval, all right? Intersection means that you trying to add even the numbers here in between 1, 3, and 5. All right, for 5, we know why there's a problem, because property number 3 says the limit is not equal to f of 5. All right. Let's do this example. All right. Where are each of the following functions discontinuous? I'm asking you where they're discontinuous. Let's look at the first one. The first one is very obvious that for x equals to 2, so look at this bottom piece. You can't divide by 0. So if x equals to 2, automatically it's going to be discontinuous. So we know already it's discontinuous at 2 because f of 2 is undefined because you can't divide by 0. Let's look at the second one, B. Where is this piecewise function undefined? Again, you can see there's a problem here. Why? Because if you take the limit as x approaches 0, it does not exist. Remember, the limit as x approaches 0, you're going to focus on this top function. Because we talk of limits, you don't include the number a itself. In this case, a is 0. You don't want to use 0 itself. You want 0 from the left or from the right, so we're going to focus on the first function. The limit as x approaches 0, 1 over x squared, you can see is undefined. All right, is 1 over 0 squared is completely undefined. So there we go. So property number 2 fails there. But if you look at C, so C here is a very tricky one. For C, f of 2, all right, someone wants me to repeat B. So for B, if you sketch 1 over x squared, let's just do a quick sketch, you get a function, so you get to get a function that dies down like that, all right? And it happens on both sides. So whether x is positive or negative, you're going to get this kind of function, all right? Because your output, they always have to be positive. Now ask yourself, what happened when you're approaching 0? You see, when I'm approaching 0 from this direction, look at what happened. This curve is heading towards positive infinity. If I'm approaching 0, as x approaches 0 from the left, look at what's happening to the curve. The curve is going up again towards positive infinity. You see, the limit as x approaches 0 does not exist. So property number 2 fails. Therefore, we say it's discontinuous at x equals to 0. All right. I hope you're happy now with B. Now for C, C is a tricky one because the first condition for continuity is f of a must be defined. F of 2 is 1. So condition number 1 is fine. Condition number 2 says a limit must exist. All right. Now, if you check the limit from the left and the right, definitely it exists. Now, the challenge is the limit from the left and the right the same as f of 2? The answer is no. So property number 3 actually fails for C. All right. And then for D, we just call this the greatest integer x, or the greatest integer function that is less than or equals to x. All right. So this one generally is a discontinuous function because it actually, so you're going to get this kind of discontinuity. We actually call it a jump discontinuity. So if you try to sketch it, it's going to look like that. And generally, this is a problem because if you check the limits at any number from the left and the right, they actually differ. All right. So in that case, the greatest integer less than or equals to x is actually a discontinuous function. This function is actually a discontinuous function. All right. So let's look at the solution here. We know from the first one, f of 2 is not defined, so you don't need to bother testing the limit. You know already it's discontinuous at 2. If you look at the second one, the limit as x approaches 0 does not exist. I sketched the graph and I showed you that when you approach 0 from the left or the right, you're heading towards positive infinity. So that limit does not exist. Property number 2 for it means it's discontinuous at 0. For C, f of 2 is equals to 1 is defined, but if you look at this, the limit as x approaches 2, or you can factor. Remember, when I give you limit, I say if direct substitution fails, try and see if you can factorize. So if you factorize there at the top, x minus 2 at the top cancel with x minus 2 at the bottom. So this guy and this guy cancel. You're left with x plus 1. Now, if you put x equals to 2 in there, you just get 2 plus 1 is 3. You see, condition number 3 in that phase that says the limit is supposed to be equal to f of 2. F of 2 is 1, but we computed the limit and it gave us 3. It means there is a problem. All right, so these two numbers here are different. Again, it means it's discontinuous at x equals to 2. All right, there we go. You can see it's 3, but this statement here is not true. All right. Now, for the greatest integer function I've already mentioned, is always discontinuous. Right? It's discontinuous for all integers because the limit from the left and the right will always be different. So in that case, it will always be discontinuous. So look at the first one there. You see there you have the discontinuity. There's an open dot there. Automatically, when we see an open dot, that means it's discontinuous at 2 because f of 2 is not defined. Look at B. You see that when you oppose 0 from the left and the right, look at where you're heading to. You're heading towards positive infinity. All right. So an infinity is not a number. So once you get infinity or minus infinity, what does that mean? It does not exist. Don't give me a limit and tell me it's equals to infinity. If you get infinity as an answer, just say the limit does not exist. All right. And then for C, so C is a tricky one. There you have to pay attention because f of a, or f of 2 in this case, exists. The limit also exists, but the limit is not the same as f of 2. That is where the challenge is. You can see here, f of 2 is this number down here, but look at what the limit is going to give you. The limit is actually right up there. So these are two different values, 1 and 3, and because they're different, you say that condition number 3 first, and therefore is discontinuous at 2. You can see here there is continuous everywhere else except at 2. Now, greatest integer function, you can see what's happening here. I'll just make a scenario. I'll just choose any number. Let's choose 3, for example. Let's see that why this function is always a discontinuous function. F of 3 exists. Everyone is happy with why it exists because f of 3, look, there's a closed dot here. A solid dot means f of 3 is defined. All right. But now the challenge is a limit does not exist for any integer value. So for example, if you take the limit from the right, you're going to get some number up there because this is a limit from the right. And then from the left, when you approach 3, look, you're approaching, you're somewhere down here. You see, the limit from the left and the right will always be different. That's why we conclude that it would always be a discontinuous function for all integer value x. All right. Okay, now there are different kinds of discontinuity, guys. You need to pay attention because I can, I've done it many times in the past. I can give you a question and I say, where is this function continuous? You give me where it's continuous, and I say, but if there is a discontinuity there, what kind of discontinuity it is? You tell me what kind of discontinuity it is, and I ask you, how can you fix this? So there's 3 things that you should be able to find where a function is discontinuous, tell me what kind of discontinuity it is, and tell me how to fix that problem. All right, we're going to do an example where I'm going to show you how to fix it. All right, but how do we name discontinuities? Removable, I'm just going to go back so that we discuss the discuss. So we call this the first one. So A here is called a removable discontinuity. All right, removable. When I say removable, it means that we can choose to ignore 2, so we can define the domain to be such that it doesn't include 2 and automatically works. All right. So removable means remove that number that causes a problem. All right. In this case, 2 is a problem for A. So if I redefine my domain to exclude 2, therefore it's fine. It's going to be a continuous function. So A and C, they call removable discontinuity. You can see the problem here, even at C, is still that number, the 2. So if I take 2 out of the picture, then it becomes a continuous function. All right. So therefore, it's removable discontinuity. Now B is infinite discontinuity, because you see here the limit is going towards infinity. So it's infinite discontinuity. And usually to fix this, what we have to do is to redefine the function, not the domain only. So the domain doesn't necessarily help you to fix stuff here. It's to redefine the function as a whole. All right. And then the last kind of discontinuity to discuss, this last one here, we call it jump discontinuity. You can see there, when you approach it, any number from the left and the right, you either below on the left, and then on the right, you actually there on the top. So it's jump discontinuity, right? And here they're just trying to explain the difference. So removable, because you can remove the keys to, you can remove that number that is causing the problem. All right. And then for infinite discontinuity, you see that the limit was going towards infinity. And then the last one is just called jump discontinuity. All right. And we say that, we call that because we say jump from one value to another. So it's almost like some funny stepwise function. It keeps jumping from one value to another. All right. Okay, someone say it's where the x values are equal for a jump. Okay, I'm not sure what you mean by when the x values are equal for a jump. But generally, for a jump discontinuity, just use this whole idea that you're jumping from one value to another, meaning that at 1, you'll be sitting somewhere there, and by the time you get to 2, you have another discontinuity that is right up there, and at 3, you have another discontinuity. The fact that you have discontinuity, that is jumping, is shifting from one stage to another, we call it jump discontinuity. All right. Definition. Guys, pay attention to my definition, because your test 2 most of the time is going to be testing your understanding of this definition. All right. It's not so much of you solving stuff, it's understanding. They say a function f is continuous from the right of a number. Remember, when I say right, I'm talking of one-sided limit. So from the right, for example, we're looking at the limit as x approaches a. You can see a, I put a plus there to say it's from the right. And that has to be equals to f of a. All right. Now, if I ask you to test for continuity from the right, it means you only have to test f of a, the limit as x approaches a from the right, if it exists, and if the limit as x approaches a from the right is equal to f of a. That's what you're going to test. All right. And then if I ask you from the left, obviously you need to say that the limit as x approaches a from the left is equal to f of a. Again, 3 conditions. F of a, limit as x approaches a from the left exists, and the limit as x approaches a from the left, f of x is equal to f of a. All right. Now, what does it mean for a function to be continuous on some interval? This is a very nice one. I give you an interval, not a number a. All right. So I give you some number there, maybe 3. I give you maybe a set 3, 5, 2, 3, 4, for example. Let's say they give you a set, and I give you a bunch of numbers, 2, 3, 4. Or I choose to put it like this. I say any number between maybe 0 and, let's say 0 and 4, for example. All right. Now, for an interval, you need to pay attention. Every number in that interval, so your function needs to be continuous at every number in that interval for you to conclude that it is continuous over the interval. All right. You can choose some random number in that interval, and then you conclude. And that goes to what you guys did for my test 1, because I asked you, is this function a one-to-one? And then people actually plug in the let x equals to 1, let x equals to 2, and then they started. You can't test because there's infinite possibility to test. You need to use the rules that they gave you. All right. So in this case, if I give you an interval, there's so much possibilities. All you need to do is start by looking at the domain of the function. Make sure that this interval is in the domain of that function. That is good enough reason to justify that that function is going to be continuous on this interval. Rather than you trying to tell me, okay, for x equals to 0, it works. For x equals to 1, it works. For x equals to 2, it works. If you do that, I'm going to say that the infinite possibilities between 0 and 4, although it's bounded, is still so many sub-intervals. You can't test 0.1, 0.01, and so on. So you can't test all of those. So the easiest way is to look for the domain of the function. Tell me that that interval that I gave you is part of that domain. And because a function is continuous across every number in its domain, therefore it will be continuous on this interval. You get your full marks. All right. As easy as that. I hope it's clear enough. Okay, now let's look at theorem 4. F and G are continuous at A. So I start by telling you that F and the function G, they're continuous at A. So we know already that they're continuous. And I tell you that C is just a constant. All right, the sum of two continuous functions gives you a continuous output. The difference of two continuous functions gives you some continuous output. If you take a constant times a continuous function, it's continuous. The product of two continuous functions is continuous. And now the quotient, guys, there's some extra condition for quotient. The quotient of two continuous functions is continuous, provided that that bottom piece there, so g of a is not equal to 0, right? Because you can't divide by 0. So whenever you're dealing with quotient, you need to pay special attention with the fact that you can't divide by 0. All right. Now, if I use the idea from theorem 4 and definition 3, I can now come to a conclusion that any polynomial is continuous everywhere. That is, it is continuous on the set of real numbers. All right. So if I give you a function and it's a polynomial, I say, is this continuous or not? Just tell me, because you know the theorem now, that a polynomial is continuous on the set of real numbers. All right, polynomial is continuous everywhere, the set of real numbers. Now, for a rational function, remember the definition of a rational function? It's a function given by p over q, where p and q are polynomials, and the bottom function there must not be equal to 0. All right, so you can have x value that makes the bottom function to be 0. Now, we say a rational function is continuous wherever it is defined. Very important. So a rational function is only continuous in its domain. So in conclusion, what I can tell you today is every function is continuous within its domain only. All right, its domain. So if I ask you where is this function continuous, indirectly I'm asking you tell me what the domain of the function is. It's as easy as that. For example, let me just make it quick and clear. I give you root of x, for example, and I say where is this function continuous? Indirectly, what am I asking you? The domain, because I say every function is continuous on this domain. What's the domain for root of x? You know x needs to be greater than or equal to 0. X cannot be negative. So it means that your answer will be x element of real number, x greater than or equal to 0. All right, you can give me like this, it's fine. Or you can give me interval form where you put square brace, it says 0, and you say infinity, open bracket. Remember, infinity is not a number. I see some of you try to put square braces when you're talking about infinity and infinity. Never do that, ever. All right. So this is a very good example. Root of x, we say, where is it continuous? You look at the domain. It says continuous for all x element of 0 to infinity. Done. It is just that. And this applies for every function. For a polynomial, what is the domain of a polynomial? X element of real number, hence, is continuous on the set of real numbers. There we go. All right. An example here, let's look at volume. All right. So this is just a volume of a sphere. 4/3 pi radius cube. Notice it. As radius increases, volume increases. All right. And we say that this is continuous where on the set of real numbers, because this is a polynomial. All right, I just replace x with r in this case. So it is a polynomial with degree what? Degree 3. Remember, we said the degree of a polynomial is just that highest power of your variable. All right, in this case, my variable is r. The highest power of r is 3. Therefore, it's degree 3, polynomial of degree 3. Again, how about this one? It's a parabola. It's also a polynomial. Therefore, it's continuous where? On the set of real numbers. All right, let's look at this. Now, if you look at the sine function and the cos function separately, the first thing you deduce is it's continuous everywhere for the set of real numbers. All right. So this little diagram here, what happens when I move this point P? So the point P is defined as cos x sine x. All right. Now the question is, when I rotate this, so you can treat this like some pendulum or something that is swinging up and down. So what happens when I rotate in this direction? So you can see that this P will be approaching the zero line. All right. So what happens when we move that point P and we're heading towards zero? All right. Now we say that as theta tends to 0, remember when you swing it down, this theta value is getting smaller and smaller. And by the time you sit on the x-axis, theta is actually equal to 0. So we say as theta approaches 0, what happens to that point P? You know already cos theta is going to approach 1. Sine theta is going to approach 0. Therefore, the point P approaches 1, 0. All right. Guys, if I ask you any question at test, don't panic. Just don't look at a diagram and feel intimidated. Just read, just look at the maths that I'm trying to show you. Use common sense, all right? There's an angle there. You know already, once you're going in this direction, that angle will be getting smaller and smaller. By the time you hit this x-axis, I'm sitting at 0. If I cross the x-axis, let's say I'm somewhere there, it's now in the negative side, all right? So you're now going to have negative theta, all right? So here we say that the point P approaches the point 1, 0. Why? Because the limit as theta tends to 0, of course, of theta you get 1. The limit as theta tends to 0 of sine theta you get 0. Hence we can conclude that the point P is going to approach the point 1, 0. All right. Now, how about the tan function? All right. For the tan function, if you notice, tan is defined as sine over cos. Tan will be continuous everywhere except whenever cos of x is equal to 0. Remember, you can't divide by 0. And if you look at the sketch of the tan graph, you have vertical asymptotes, right? So you get that kind of shape. You have asymptotes here and there, and then you have that kind of shape. So where are these asymptotes? These asymptotes, they occur wherever cos of x is equal to 0. Why? Because you can't say sine of something divided by 0. We can't divide by 0. And where exactly does that happen? It happens for every odd integer multiple of pi over 2. Remember, cos of pi over 2 is 0, right? So for every odd integer multiple of pi over 2, tan is going to be undefined. So you're going to get some infinite discontinuity. Again, I'm using the word infinite discontinuity because I'm reminding you what kind of discontinuity this is. I told you need to know how to define the discontinuity. I can ask you, what kind of discontinuity is this? You should be able to tell me. Why is this infinite? Because, for example, look at pi over 2. We're heading towards positive infinity. Look at minus pi over 2. We're heading towards negative infinity. So we call this infinite. All right, you're heading towards infinity there, heading towards minus infinity. This is infinite discontinuity. All right. If you had a problem only at a specific number a, you will say removable. Because if I take away that number a that causes a problem, everything works. All right. All right. So theorem 7 is just a reminder of what I've mentioned earlier, that the following types of functions are continuous at every number in their domain. All right. So any function is just continuous at every number in their domain. Polynomial is continuous in a set of real numbers. Rational function, again, you focus on the domain. Make sure the bottom piece is not equal to 0. Trig function, again, focus on the domain. We've seen that for a tan function, you have a problem. Obviously, it means for a cot function also, you're going to get a problem. You're going to get those infinite discontinuity. And then for root function, I've already done an example. For example, we saw root x earlier. Again, you focus on the domain, all right? Now, there's something I need to mention. I know most of you will be surprised. If I give you cube root of x, all right? It's a root function. And then I ask you, where is this function continuous? Guys, don't tell me that for x greater than or equal to 0. Be careful, all right? there is a cube root of a negative number. So cube root function, the domain is the set of real numbers. All right, so you need to pay attention. So for odd, so in summary, I'm just going to put n there just so that everyone is happy. For every n root of x, if n is odd, the domain is the set of real numbers. If n is even, the focus will be that this bottom piece has to be greater than or equal to 0, or everything inside the root has to be greater than or equal to 0. So pay attention to that, because I saw in my test, people were saying all kinds of stuff that are not true. All right. So cubic function, the domain is the set of real numbers. All right. Because the n there is odd. You can see it's an odd number, the 3. So it makes it a set of real numbers. If it was even, we're going to say x is greater than or equal to 0. Now, if the root appears at the denominator, so let's say I give you some function, I'll just say f over some other function that happens to be a root function. So let's assume that f is just any function. It can be any function at the top. Now be careful, when the root appears at the bottom, you don't say greater than or equals to. So x in this case needs to be greater than 0. You can say equal to because it's at the bottom. You can divide by 0. Right. We're going to use the same idea to solve this problem here, which is a very nice example you need to be able to remember. I asked you, where is this function continuous? You can see it's a combination of natural logarithmic function, you have trig function, inverse trig function, and they have a polynomial there at the bottom. All right, where is the function continuous? Some of you, this is what you're going to do. You're going to quickly focus on the bottom piece here. You say x squared minus 1 cannot be equal to 0, and your conclusion will be that it's continuous everywhere except when x is equal to 1 or minus 1. All right, if you do that, your answer is incorrect, completely wrong. All right, I'm going to tell you why. Because you fail to consider this piece here, this little piece here. All right, you fail to consider the ln function. There's no ln of 0 or ln of a negative number. For a ln function, x has to be greater than 0. Do you see that? So you see where that restriction is coming in, where 0 here is coming from. Because I also need to consider the ln function. I can't just say x cannot be 1 or minus 1. Yeah? If you say x is not 1 or minus 1, you say that x can be minus 2. Yeah, that's what you're trying to say, which is not true, because ln of minus 2, for example, does not exist. Ln of 0 or any negative number is undefined. Therefore, you need to consider the domain of each of these functions. So in conclusion, you need to look for the intersection of the domains of all the function that makes up that function f of x there. All right. So look for the domain for tan inverse function. Some of you actually are safe, you're scratching your head. What's the domain of tan inverse function? You need to do a quick sketch. You know, tan inverse is going to be divided at pi over 2 and minus pi over 2. So you have pi over 2 down, you're going to have minus pi over 2. That is where you get your horizontal asymptotes. There you have a shape that actually looks like this. All right, so you're going to get that kind of shape. Notice it, this is defined for any x value, right? You can see it's valid for any x value. So the domain for that tan inverse function there is fine, it's valid everywhere. The ln function, you have a problem because x needs to be greater than 0. And then at the bottom here, x cannot be 1 or minus 1. So if you take the intersection of this interval, you see it will be from 0 to 1, union from 1 to infinity. Again, I'm using union. I gave you guys inequality in my first test, and people kept just using intersection all over the place, which clearly tells me that they don't understand. All right. Union means that I have different intervals. They're not continuous. Intersection is more or less, you're talking of continuous interval. For example, if I say x lies between maybe 2 and minus 2. All right. So indirectly, this is an intersection. It means that x is less than 2 and x there is greater than minus 2. So it's an and, it's an intersection. Because you can see it's one interval. It's for minus 2. It's for minus 2 all the way to 2. So it's a continuous interval. All right. That is only when you're allowed to use intersection. Or you can see the different interval from 0 to 1 and then from 1 to infinity. right? With the 1 itself not being included. You see, I'm excluding the 1 itself, all right? All right, this other property, which I'm going to explain now, guys, is a very take note, all right? When I say very take note, you need to remember this, all right? And the way I'm going to ask you this kind of question in my test or in the exam is, I'm going to tell you to use continuity, because if I don't use that wording, use continuity to solve this, people will come up with all the funniest answers in the world. So watch out. If I ask you a question and I say use continuity to solve this, indirectly I'm asking for theorem 8. All right, I hope you remember that hint. So they say a function f is continuous at b, and then they give you the limit as x approaches a of g of x is equals to b. So you see that this function is continuous at the limit of g of x as x approaches a. All right. Now we say the limit as x approaches a of f of g of x is just f of b. What does that mean? It means that I can take the limit in. So the limit of f of g of x is the same as f of the limit of g of x. All right. Why can I take the limit in? Because I already know that the output from this limit is in the domain of f. Very important. All right. You can take the limit into the function only if you show that the output, the result from this limit, is actually in the domain of your function f. All right. Let's look at an example. Right. This is a nice example. All right. I say evaluate the limit as x approaches 1 of sine inverse of, guys, another thing I need to mention is this sign here means inverse, not reciprocal, guys, please. If I'm asking for reciprocal, I mentioned it before, I'll literally say 1 over something, or I'll enforce a bracket there and put the -1 outside to tell you that's reciprocal. So please, if you see stuff like this, I'm talking of inverse, all right, not reciprocals. It happens every year, almost every year in my exam. I'm not saying that I always ask this kind of question in my exam, but every time when there's an inverse question in my exam, I see reciprocal solutions. Even for my test too, a lot of people just give me the reciprocal. Probably those that are not in class today, they'll give me reciprocal. All right, they'll say 1 over sine is cosec, and then they start doing some funny stuff. All right, and they get a beautiful 0 in that process. All right. Now, what is your explanation here? Like I said, if I ask you this kind of question, I'm going to say use limit to evaluate this, all right? And what you need to tell me is that the arcsine function is a continuous function, all right? So arcsine function is a continuous function, meaning that it accepts every number within its domain. And in that case, you're going to take the limit in, all right? Why am I taking the limit in? Because I know arcsine of the limit of this actually exists. All right. Remember, if I simplify this, look at what I get. I end up with the limit giving me half. And arcsine of half exists. All right. So indirectly, we say that half is in the domain of your arcsine function. All right. So in that case, you're allowed to take the limit in. All right. But because you don't know in advance that that whole calculation might lead to half, you start by telling me that the arcsine function is actually a continuous function, meaning that you need to tell me what does that mean. It means that for every number in this domain, the arcsine function will be continuous at that number x. All right. So arcsine function is continuous for every number x in this domain. All right. Then take the limit in. Look how I simplified this guy. Please don't. I told you before. When I give you a limit, what do? You try direct substitution. If it doesn't work, what do? Look at the function. If it's root functions, for example, like what we have here, 1 minus root of x, try and rationalize. All right. If it's some polynomial, try and factorize and see if some factors are going to cancel out. Play around with your function until nothing works before you conclude that it does not exist. Don't be quick to substitution and tell me it does not exist. You get a 0. All right. In this case, I can multiply the top bottom by the conjugate of this function there at the top. So 1 minus root of x, you just multiply top bottom by 1 plus root of x. Remember, conjugate means you just change the sign. So if it's 1 minus root of x, you use 1 plus root of x, multiply top and bottom. And if you do that, it actually works. All right. And you can see that the limit is x approaches 1 is half. And in that case, arcsine of a half is pi over 6. And it works. All right. But what was my first statement? Arcsine function is a continuous function on every number in its domain. All right. Another theorem. Now this is composition. We look at composition function. They say if G is continuous at A. Remember, by now you should be ringing the bell already when I say G is continuous at A. You know all those conditions, right? It means G of A is defined, limit as x approaches A exists, limit as x approaches A is equals to G of A. All right, three things, three conditions for a function to be continuous at the number A. All right. And then I say G is continuous at A, F is continuous at G of A. All right. Then the composition F of G, remember F of G means you're going to take the G function, put it inside the F function. Right. So the composition function F of G is also continuous at A. All right. Intermediate value theorem. This is something else you need to know. Suppose F is continuous on a closed interval AB. See, the endpoints are included because it's a closed interval. We say let n be any number between f of A and f of B, where, take note, f of A must not be equal to f of B. So n is some number between f of A and f of B, but don't use the endpoints to say A and B. So you can't use f of A or f of B. So they have to be different, all right? Then they say there exists a number C in the open interval such that f of C is equals to n. All right, and this is very useful when I ask you, for example, to show that, for example, a polynomial has a root, all right, or 2 roots or 3 roots, and so on. Let's look at this. Now, these are different ways in which we can choose our n. So you see, n here is just n there can be chosen to be just one value between f of A and f of B. And your number C, you see, it lies between the open interval A and B, and here we only have one choice of C. All right. But now, if you look at case number B, n can be taken more than once. So, for example, for C1, you see C1, I'm just going to highlight that. C1 there leads to the same n. C2 there leads to the same n. C3 in this case leads to the same n. All right. Very important example 5, right? So I'm going to, I always say this, and then when such question come my test, people act like they've never seen intermediate value theorem. All right. Very, very important example 5. Show that there is a root of the equation between 1 and 2. All right. I'm telling you that. Yeah, you need to tell me, you need to show me that this polynomial function or this cubic function actually has a root in between 1 and 2. All right. The basic understanding of showing that you have a root, I'm going to draw a little sketch for basic understanding. All right. Let's assume that I have a curve. Just gonna all right, let's assume this is some weird curve. Now, do you agree that this curve has a root? Remember, the root happens where that function, it happens at that x value that gives you 0. The fact that it's going to cut, it cuts x-axis at any point means that it has at least one root. All right. For a function that has more than one root, I'm just going to illustrate using a different sketch. You're going to have stuff that look like that. So a function like this, you're going to see that it's going to have 3 roots. All right. So the basic understanding here of to show that you have a root between 1 and 2, you need to be able to show that between the number 1 and 2, that curve of yours or that imaginary curve needs to cut the x-axis. All right. It needs to cut the x-axis between 1 and 2 to show that there is a root. So indirectly, your n in this case is 0. All right. All right. First step, guys, this is how I expect you to tackle this problem. When I say how, it means verbatim. This is a process, step-by-step process how I want you to solve this if you get asked. Or if you most probably be asked, so I'll just say this is how you have to answer it. Let f of x be this polynomial. All right. Don't just say f is a polynomial. You just start telling me all kinds of stuff. Start by telling me what f of x is. Let f of x be the polynomial. We're looking for a number c between 1 and 2. All right. You want c to be between the open interval 1 and 2, such that f of c equals to 0. Remember, when I use the word root, what does that mean? It means at x equals to c, where c is the root, my function is to give me 0. It has to be equals to 0. That is only when we say x equals to c is a root. All right. So in this case, you know what a is. A is 1. Your b is 2. Remember, those are a and b. And your n is 0. Remember, your n there is this number here. You want f of c to be equals to n. In this case, your n is 0. All right. Yes, this student here did something really good. A sign change tells you that there is a root. Yes, if you take f of 1 and you take f of 2, you see a sign change, it means that you have a root. All right. It's similar to what I was just telling you. Let's assume that that is my curve. Do you agree that the f of some x value here will be positive, while f of some x value here is going to be negative? That tells you that somewhere in between those two numbers, you have a root. All right, sign change, very, very important. Sign change. So after doing this, so let f of x be that. Your next step is, you don't have to write all of this long stuff here. I assume that we all know what a, b, and n is. Just tell me that f of 1, show me the sign change, very important. F of 1 gives me minus 1, is negative, it's less than 0. F of 2 gives me a positive answer, which is greater than 0. There is a sign change. You can see that 0, so f of 1 is less than 0, but it's actually greater than f of 2. That is, you have your n is 0. So your n lies between f of 1 and f of 2. All right. So remember, n needs to always lie between f of 1 and f of 2. It makes sense, right? I'm going to show you now quickly. I know there's still some doubt. Why do we have that statement there? My one input is minus 1. The other input is 12. You see that n, you see n is 0. And we can confidently say that n lies between f1 and f2 because 0 lies in between these two numbers. 0 lies somewhere in between these two. Therefore, we can say that n lies between f1 and f2. Now, this is where you need to use intermediate value theorem, right? You say since f is a polynomial and it is continuous on this closed interval, guys, be careful because not every function is going to just work like that. We know that you've mentioned the fact that f is a polynomial, and by saying that it's a polynomial, you're saying that the domain is a set of real numbers. It means it's continuous everywhere, all right? Automatically means it has to be continuous on this closed interval, all right? Because it's a polynomial, all right? Be careful if the function changes. Don't just come and give me, oh, it's a polynomial, it's continuous. No. You need to find the domain. You need to see that that closed interval is part of that domain, all right? So because it's a polynomial, we know polynomial is continuous on the set of real numbers. Automatically, the set that interval 1, 2 is part of real numbers. All right. We said therefore, by the intermediate value theorem, there exists a number c in the open interval. Guys, please don't swap these two here. I've seen it many times. Some people say, oh, it's continuous on the open interval. There exists a c in the closed interval. But once you start swapping things, I assume that you did some cam work. You don't understand. Oh, all right. So it's continuous on the closed interval. And then we say there exists by the intermediate. So this IVT means intermediate value theorem. Please just write the full intermediate value theorem. Because if you write IVT in my test, I will assume that I don't know what you're saying, and I will circle it and say, what is this? All right. So, right, intermediate value theorem, there exists a c in the open interval 1, 2, such that f of c is equal to 0. All right. Again, why am I using 0? Because we're talking of root. Root means f of c. You want f of c to be equal to 0. So your n in this case is 0. All right. In other words, you say that the equation has at least one root c in the interval 1 and 2. All right. I hope everyone is happy. Please, this is the end. Please make sure you do the TAT. The last TAT that I uploaded covers up to week 9, so it covers up to 2.5 actually. Make sure you can do the continuity question there. Like I said, I'll instruct the tutors to use their tutor time to give tutorials. So please just make yourself available whenever they're giving that. And I'll advise them to always record it and share in the WhatsApp group just so that everyone can see the recording in case they can actually attend. But I'll advise you to attend so that you ask your questions. And some of you would take my touch serious or take things serious once I release your marks tomorrow. You're going to notice that you really need to start working. All right. Okay, someone is not part of the WhatsApp group. If you check on the, just send me an email and I'll send you the link, or someone else that is on the group can just send their number for the tutor to add them. Or another way of doing it is just if you check the admin folder, there is a document, a PDF called consultation. The links are all there for Asma and Asmi. All right. So if you're checking the admin folder, you see consultation PDF. Open the PDF. The link to the WhatsApp group is there. If you click there, then the tutor will be able to add you. All right. Or like I said, any of you that is in the same group as a student, you can just give their numbers in the group and the admin is going to add them. But you need to specify if you didn't ask me or ask me, because I think for now there are different groups for asthma or ask me. Okay, I'm just going to stop